Hey, Physics 1. I'm going to go through some of our notes covering waves. So I'm going to introduce the topics of waves, what they are, give you some classifications, tell you a little bit about like some descriptions we can use for waves, some equations and mathematical processes we might use when we're trying to describe waves. Just give you like a general overview. The notes that I'm going through are on the course website, so you can reference them there. In addition, there's some simulations, there's some reference videos, some demonstrations that I would generally do as part of this introduction. So if we were all in a room together, they would be mixed in with some videos and other stuff. So I'm going to put those things separately on the course website for you to be able to see and kind of get to those things when you need them. I'm just going to go through the notes part of this today. You can kind of go through this at your own pace, and we'll kind of pace our way through this as well. You don't have to watch all of the notes at once. As you're working on quest problems, you may find some of the simulations and demonstrations and activities are helpful for understanding waves. It is something that really benefits from like having visuals and moving pictures to go along with. So the notes are kind of going to give you an overview so we can have the right vocabulary to talk about waves. So we should probably start with what waves are. So again, we have the right vocabulary to deal with them. So a wave is a disturbance that transfers energy without transferring matter. Okay, so disturbance that transfers energy but not matter. So if you have a wave, there's energy moving from one place to another, even though the particles themselves don't move overall. So they might oscillate, they might move back and forth a little bit, but their position, their average position is not changing. There are two main types of waves that we're going to deal with. There are mechanical waves, and there are electromagnetic waves. That's it. So those two types of waves are going to cover pretty much everything out there. And what separates them is, not particularly, complicated. It's just has completely to do with the with how they travel. So mechanical waves require a medium. Electromagnetic waves, no medium. We're going to focus first on mechanical waves, things that are waves that require a medium to travel through. So water waves, for example, when you have a wave on the ocean, energy is moving from one place to another, but there's not an overall large mass movement of particles from one position to another. The water waves tend to have particles oscillate back and forth, but their average position is not really changing much with time. A wave at a football stadium or something like that, people put their arms up in the air, that's energy moving from one place to another, but the people whose arms are moving up in the air, they're actually not moving one seat down. They're staying put. So they are the medium through which a wave is traveling. Electromagnetic waves are a little bit different. Electromagnetic waves, if you maybe have heard of the electromagnetic spectrum from a previous science class, the electromagnetic spectrum involves X-rays, radio waves, microwaves, visible light. We'll talk about the electromagnetic spectrum later. But electromagnetic spectrum, basically all forms of electromagnetic radiation are waves, but can travel even through a vacuum. And if they can travel through a vacuum, that means there's no medium there for them to move through. They are, however, still oscillations that transfer energy. And so we classify them as a type of wave. All right. I'm going to skip some of these. I have some videos here that are not going to run right now. But what we can talk about is our main categorization of waves. So we already talked about separating waves by the type of medium that they travel through or don't travel through. But we can also classify waves based on how they oscillate. Remember that waves involve oscillations of particles, but not an overall motion of particles from one place to another. So there's three different categories of waves. The first one is a transverse wave. When you have a transverse wave, the wave is propagating in such a way that the movement of the particles is perpendicular to the movement of the energy. So, wave propagation with the particles of the medium moving or oscillating perpendicular to the, let's see, direction of the energy flow. So if your wave is propagating in that direction, then your particles might oscillate up and down. I'm going to give you guys a simulation that's going to help you visualize this, what we mean when we say we have a transverse wave. If we have, say, a rope or something like that, if you've ever taken like a rope or a string and you set it down flat on the floor and then you lift the rope up, just like whip your hand upward and then back down again, you'll see a peak come through on that medium, where the medium is the rope and the wave is that bump, that propagation, or that disturbance within that medium. And that would be a transverse wave. Again, we'll have some demonstrations and videos that you can look at later. A longitudinal wave is a different type of wave. Longitudinal waves are waves where the particles in the medium move or oscillate in a direction parallel to the direction of the wave front, or the energy motion. So the wave propagates with particle motion parallel to the energy or wave motion. It happens through having compression and then separation of particles in the medium. So if you have a bunch of particles that are spread out, you may get some of them that squish together a little bit and then push apart, back and forth. And that back and forth particle movement that propagates through your material is called a longitudinal wave, or sometimes a compression wave. Our main example of this that we'll see over and over again would be sound. Sound waves occur when air molecules compress and then pull away from one another, and that wave motion, that interaction between particles that are near one another, propagates through space. All right, so here's just a view of what this compression and lower density regions might look like when you have a longitudinal wave, or a sound wave as an example of a longitudinal wave. We have special names for these. The compression zone in one of those waves is the part in the longitudinal wave at which we have that maximum density of the medium. And then we have rarefaction as a part of the longitudinal wave where that medium is at a minimum density. So we get these alternating regions of high and low density and high and low pressure if we're talking about air. And as sound moves forward in this direction, you'll get these oscillating segments of these compressed air molecules. They kind of bump and push around the molecules and the regions nearby. So, in order for us to talk about waves, we probably want to have some vocabulary to describe the properties of waves. So first, general property that we might want to think about with waves would be amplitude. So amplitude is our maximum displacement from the wave from its equilibrium position. So a taller wave, it has a higher amplitude. In order to increase the amplitude of a wave, we need more energy. So the amplitude is going to be related directly to the energy associated with the system. In order to make something oscillate up and down at a higher amplitude, you need to add extra energy into the system. The next wave property, or wave, descriptor that we want to deal with would be wavelength. So you may be familiar with wavelength already. It's possibly something that you've seen described in another class before, but we define our wavelength as the distance from one point to another on a wave as it repeats. So one full oscillation. So this would be one full wave because we go from the starting maximum height, we go all the way through this cycle, and we go back to where we started again. That's not the only way I can measure that wavelength. I could measure that wavelength from another point. So if I pick that as my starting point, I go through one complete cycle, and then I wait until I'm back at that same position in the cycle again. That would also be another way of representing the wavelength of that wave. I could start here, and then I would need to go through this complete cycle until I'm back at that same position again. This would be one wavelength. Our wavelength is very much a measure of length, and so when we use that symbol lambda to represent wavelength, we typically use SI units of length to describe it. So our SI units of length would be meters. So we measure our wavelength typically in meters. Now, depending on what kind of wavelength we're dealing with, we might have to measure it in kilometers, we might need to measure it in nanometers. So this is a point where you might need to go back and forth and use your base SI unit conversions in a few different cases here. Now, a few other vocabulary points here. Sometimes we call the top of this wave, like its maximum point, we have a special name for that. We call that a crest. And sometimes we call the bottom of this wave a trough. I don't know, it's all that important that you recognize those, but that trough is the low point of the wave, and the crest is the higher up point. Sometimes you'll hear those terms used. All right. The other descriptor we might see dealing with waves would be frequency. Frequency is basically the number of repeating occurrences per unit of time. So if it takes, say, 1 second for this wave to oscillate back and forth, this would be a higher frequency because I get many, many, many more oscillations in a given time period. And this would be a low frequency because I have fewer complete oscillations in a given time period. So notice that the frequency must be inversely related to wavelength. Oops. Because this is a relatively short wavelength, whereas here, all else being equal, this is a longer wavelength for that wave. So this is a high frequency and this is a low frequency. Now, if I want to talk about how fast a wave moves, I have a few different ways that I can describe that. I mean, wave speed, though, is really just thinking about speed as we've thought about speed before. Thinking about distance divided by time. So if I want to think about a mechanical wave moving through some medium, then I can think about, well, how fast does the front of that wave, or does a crest or a trough on that wave, how long does it take the crest of a wave to get from point A to point B? If I can take that distance, divide by time, I have my wave speed. Typically, when we're dealing with mechanical waves, the speed is completely independent of amplitude, frequency, and wavelength. It doesn't matter how high up that wave is, doesn't matter how fast it's oscillating. What's going to determine the speed of a mechanical wave is going to be the medium that it's traveling through. Because for a mechanical wave, the motion of that wave is dependent on the oscillation of the particles present in that medium, and how those particles are oscillating, how quickly they're oscillating, what sort of interaction they have with their neighboring molecules. That's going to determine our wave speed. And so the medium is critical in determining what the speed of a wave is. For a given wave, we have another way of representing wave speed. I'll give you a second equation. So we have distance over time. Another way of representing wave speed is that it's the product of a wave's frequency and its wavelength. So we really have two equations that we're going to use to represent wave speed: distance over time, or frequency times wavelength. This is kinematics. This is new material here. Now, sound waves, in particular, are a specific kind of longitudinal wave or pressure wave that we're going to want to know a little bit more detail about. So I'm going to talk a little bit about sound waves. Notice that we often represent them with these up and down motions, those up and down lines that would make it look like it's transverse. But when we use this sort of a drawing to represent the sound wave, what we're really representing is the high and low density of the air. So these peaks, these crests, are representing a position where we have compression of the air, and the troughs are representing that rarefaction or that low density region. But anytime you're dealing with a sound wave, you are dealing with a longitudinal wave, one where the oscillation of these particles is back and forth, such a way that you get high density regions and low density regions in the air, as those air molecules move back and forth until they, say, run into and interact with your eardrum. So like all waves, or all mechanical waves, the speed of sound depends on the medium that it travels through. When we're dealing with the speed of sound, it might depend on the temperature of the medium. It might depend on the type of medium. So when we're dealing with sound, is sound moving through air? Is it moving through water? Is it moving through steel? The other thing it might depend on is the density. Now, it's not true that more dense material means faster sound. It's not 100% accurate. It tends to be, it kind of follows that trend to some degree, but there's really multiple factors at play. There's temperature, type, and density, all of those sort of interacting with one another. If we could kind of tease out and focus on one thing at a time, then that might work. So for example, when you go up to higher altitudes, the density of air is less, and as a result, you get a change in the speed of sound through, at those lower density. Now, of course, the temperature of the air is also a little bit cooler as you're up at higher altitudes, but again, all of these things could have an effect on the speed of sound through a given medium. If we're thinking about speed of sound in solids and liquids, in terms of numbers that you probably want to be at least somewhat familiar with, speed of sound in air, about 343 meters per second, or about, roughly 340 meters per second is usually the number I use. So that is, at 20 degrees C. Lower the temperature a little bit, and you get a slightly lower speed. Take a look at helium, though. Speed of sound in air and helium, quite a bit faster. Might be why, or I don't know if you make this connection or not. But when you breathe in helium, it sounds really, really different across your vocal cords. Water, much faster speed of sound in water, even faster in seawater. And then you take a look at metals. Sound moves really, really fast through metals. So through those solid materials, the molecules are really packed together a lot more tightly, and the oscillations tend to affect and the neighboring molecules more readily. And so when you have a lot of molecules packed really tightly together, you'll tend to see that faster speed of sound. When we're talking about sound, we might use the term pitch. I don't know if pitch is a familiar term or not, but when we're talking about pitch, we're referring to a specific wave property, and I want to make sure we can identify that. So pitch is how your ear interprets the frequency of sound. We don't use the word pitch when we're talking about, say, an ocean wave or something like that. But we could use the word frequency to describe the wave, an ocean wave, or a wave of people sitting in a stadium and putting their arms up in the air, or a wave of light, or a wave of sound. Pitch is a specific term that we talk about when we're dealing with how the human ear perceives frequency of sound. Loudness is something completely different. Loudness is how we perceive the amplitude of sound. Got a little ahead of myself. We don't necessarily talk about loudness of an ocean wave or loudness of light, but we do talk about loudness of sound. And that just means sound that has a high amplitude. So this would be an example of a quieter sound, whereas this would be a louder sound because that amplitude, that maximum height of the crest of our wave is much taller. Now, when we're talking about pitch, that has to do with frequency. So this long wavelength wave here is a deeper pitch or a low pitch. Whereas this high frequency wave here, that is a higher pitch. So this would be a higher pitch sound, and this is a lower, deeper sound. And notice it has nothing to do with the loudness at all. Those are completely separate. All right, I'm actually going to skip this. Our third type of wave, I guess I'll talk about it a little bit. Our third type of wave is a surface wave. We're going to focus on transverse and longitudinal waves. That's basically all I'm going to talk about from here on out. But surface waves, well, let's think about it this way. Transverse wave oscillates up and down as energy propagates forward. Longitudinal waves oscillate back and forth as energy propagates forward. A surface wave is like a combination of those other two. So one way to think about it is that transverse waves are like waves that have y components only, and longitudinal waves have x component only of their oscillation of motion of the particles, and surface waves are like x and y motion both. And so with a surface wave, you might get a combination of up and downward motion and forward and back motion. So it might actually look like a circular motion. So when you have a surface wave, and this is really what ocean waves look like, you might get a particle that will tend to kind of oscillate back and forth. So it's moving forward and backward and up and down at the same time. They'll move in like this rolling sort of motion in a cycle. But a surface wave itself is like longitudinal. I keep doing that. Plus transverse motion. Okay. A lot of real motion and real waves in materials are actually surface waves, but sometimes it's easier to simplify and to think about them as just one type of motion. But we're going to be focusing on light, which is purely a transverse wave, and sound, which is purely a longitudinal wave. And so we're not going to have to look too much in detail at waves that have a combination of those motions. I will save that for some future physics course for you. We're not going to get to do this right now. Maybe another time. All right. Waves can reflect off of surfaces and bounce off of surfaces. Just like if I take like a tennis ball and throw it at a surface, it can bounce back at me. A propagating wave can do the same thing. And you're going to be able to see that in some demonstrations that you're going to do later on. So there is a wave simulation link on the topics page where you can have a fixed barrier at the end and you can see the wave bounce off of the surface. I will give you guys a chance to do that later, but waves can reflect off of surfaces. When a wave strikes a medium boundary, so like hits the end of a medium, it can bounce back into the original medium. Completely reflected waves should have the same energy and the same speed as the original wave. But here's one weird thing that happens when you have a fixed end reflection. So for example, if I have a string and it's tied in a knot here against a surface, and this knot can't move. As this wave propagates in and gets closer and closer to this surface, when it bounces off, it will invert. And you'll see this in simulations, and you can see it too if you try it out. You can take a string, tie it to the end of a chair or something. You can actually see this effect. And this wave will invert when you have a fixed end. So when real waves hit a boundary though, you will see that absorption, but real waves will sometimes be absorbed a little bit as you lose some energy in that collision with a medium. When we do simulations and stuff, we're going to look at sort of idealized waves typically. All right, let's see. All right, quick question to think about. If you lower the frequency of a wave in a string, you will A, lower its speed, B, increase its wavelength, C, lower its amplitude, D, shorten its period. Give it some thought. So let's take a look at what our equation is for waves. Wave speed equals frequency times wavelength. And if I lower the frequency for a wave in a string, I'm going to assume that I'm not changing the string itself. I'm not changing the medium. And so this is constant because it depends on the medium. If that's not changing, then lowering the frequency is going to have no effect on its speed. It's also going to have no effect on its amplitude. It does, however, increase its wavelength. So we're going to go with B here. Because if our medium stays the same, that means our speed must stay the same. So if I lower frequency, I'm going to increase the wavelength. What is period here? Now, we had talked about period of a oscillation back when we did our whirligig lab. I know it's been a while, So I'm going to give you a quick refresher now. Period is the amount of time it takes for one oscillation to occur. That's different from frequency. Frequency is oscillations per second. So let me write this out for you. I think that's worth noting. So frequency equals oscillations per second. Period is seconds per oscillation. See the difference? They're not the same. Frequency is going to have units of inverse seconds. Seconds to the -1. Whereas period has units of seconds. Sometimes we call these units of inverse seconds hertz. So I measure the frequency of a wave in hertz. So if it has 5 oscillations per second, then it's going to have a frequency of 5 hertz. But if I want to know the period, how much time each of those oscillations take, I'm doing the inverse of that. If I have 5 oscillations in 1 second, then in 1 second I have 5 oscillations. So that means my period, the time it takes for one oscillation to occur, is 1/5 of a second. So just to summarize that and shorten that up, frequency is the inverse of period. They are related to one another. They're inverses of one another. All right. I think this is a good place to stop. I'm going to stop here now that we've defined some terminology for waves. Our next video is going to be about wave interference.